This video will be on section 9.4, which is partial fractions. So I'll begin by talking about what partial fractions is, the idea of it. Then really when you do partial fractions, there's two things to do. You have to set it up, and then you have to actually solve it. And then really, once you know how to set them up comfortably, solving it is very similar every time. Sometimes it's super short. Sometimes you get a system of equations to solve, which is why it's in this chapter. But if you don't set it up right, you cannot get it right. So that's why it's broken off into these two separate sections instead of just doing it. Just to really emphasize how that setting them up is important. All right, so the idea of partial fractions, I have an example here of what we're trying to do. So the idea of partial fractions is pretty much breaking apart a simplified fraction. So the example I have here, the 9x plus 3 over x squared plus 2x minus 1, the single fraction, into its separate parts like this. And you know, we're used to taking something like this, getting a common denominator, writing it over one fraction, and thinking of that as simplified. But there are topics in calculus where doing stuff with this is not a good idea and may not even be possible in some examples, but doing it with the broken apart side is much easier. So once again, the idea is going to be start here and working backwards is exactly what partial fractions decomposition is. All right, so I want to kind of outline these steps here because the steps we take to set it up, we won't really be able to see how to solve it in this example, but the steps you take to set it up are the same every time, depending on a couple factors. All right, so ordinarily what we do is we get a common denominator. This one, if we wanted to solve it, since our denominators are completely dislike, we have to multiply the opposite fraction by that denominator. So the 3 over x minus 1, that's why we multiply it by x plus 3 on the top and bottom. The 6 over x plus 3, we multiply that by x minus 1 on the top and bottom. And we get to this step. And then from this step, we notice since we have the common denominator here, we can combine them into one fraction. Now what I did here, because this is the way the problems will typically be written, is it will be multiplied out already. And then we add the numerators together. And to get the 9x plus 3, I just distributed the 3 in the first one, the 6 in the second one, and combined any like terms there. All right, but the idea with working backwards is really to look at this first and then second step here. All right, so, and even more direct, I can just kind of look at the second step. So what happens to go from here to here? Well, what you want to notice is that if we had factored the denominator, if denominator factors to x minus 1 times x plus 3, that's exactly each denominator over here. So the beginning part starts with that. We want to factor the original denominator. And this is really outlined below. I'm just kind of previewing, especially because this is our easy example. It factors, and we have one or two different factors here. So we want to factor the original denominator, and then for each factor that we have, so x minus 1 and x plus 3 gets a fraction with it, and each part goes in the denominator. So we'd have two fractions, x minus 1 in one denominator, x plus 3 in the other denominator. So each factor gets a fraction. And we will see in the general rule, if there are repeated factors. So if you have like an x squared, that's like x times x, or x minus 1 squared, then you have to make minor adjustments. But we're just going to start with this easy type of example where there's no powers, there's just two factors. Now the numerators, there's no way at the beginning you would ever be able to figure out 3 and 6. The fact that 3 and 6 add to 9 is really coincidental, and then you'd still have to manage to figure out that 3. So it could be 4 and 5, it could be 2 and 7. You're not going to know that at the beginning. So the top is going to be a generic expression. And the goal of the problems when we set them up like this is to solve for the things that we're missing in the numerator. And I can't really be more explicit at this stage of a generic expression. I'll have it more explicitly written down here and talk about that, because it depends on what your denominators are. Right, but once again, the goal here, just to try to outline, we factor the denominator. Each denominator gets a fraction, and in the numerator we put something, like a placeholder that we're going to solve for. Right, so I kind of have it outlined in 4 steps of how to properly solve it up in a more direct way. We want to factor the denominator completely, as I wrote above, without complex numbers. So, if you see something like that, that would factor, but it has a complex number in it, don't do that. Usually we don't even notice something like that anyway, so you probably won't come across that, but just beware. Any repeated factors, this is important, should be condensed and raised to the appropriate exponent, right, which is something that we called multiplicity back in chapter 3. So like example here, x minus 1 times x minus 1 equals x minus 1 squared. You want to write it like that. You don't want to leave it like this, and you'll see why. And one that most people, when they see it in a problem in this section, they don't associate it with multiplicity, is if you have just x times x being x squared. We have to think of x squared as being x times x in this section. Okay, but if we have any problems like that, you'll see them below. We will definitely have a repeated multiplicity at some point though. All right, so each factor, let me use a different color, then I click on it. Each factor of the denominator will correspond to a denominator of a fraction. So that's kind of what I have above in green. Now, the one example is, what if we do have this squared? So what if we factored this and we had x plus 3, but then the x plus 1 was, or x minus 1 was squared? If a factor has a multiplicity of m, so squared, like x minus 1 squared has multiplicity 2, then it will actually make that many fractions. It says then there will be m fractions. So just from the x minus 1 squared, there will be 2 fractions. And the exponents in each fraction, you'll start with 1 and go up. So if there are 2 fractions for a factor, you would have, for this one, x minus 1, and then the other one would be x minus 1 squared. And if you had a cubed, x minus 1 cubed. But it's very rare to go past squared, and I don't think we will be doing that. I'm like 99% sure. You will see some squareds, but not cubes. All right, now the hard part to understand for the setting up, at least for me, when I started learning this, is what goes in the numerator. The numerator is a generic degree 1 less than the degree of the denominator, specifically the denominator's factor. Right? So, for example, just using my x minus 1 and x minus 1 squared again, if the denominator is x minus 1, that's degree 1. And one less degree than that would be degree 0. A degree 0 polynomial is just a number. So the corresponding numerator would be degree 0, which is just a number. If it's just a number, we want to write it generically. We don't want to try to solve the number, but we do want to give it a name. So we name it. Typically, the convention is to name them lowercase letters at the beginning of the alphabet. You can call them anything. You just don't want to call them X because we're using X as our variable. Right, so we'll see when we set up how that works. And as I go through the problems, you'll see the other examples as well. Like, what if we have an x minus 1 squared? What do we put in the denominator? There will be some things that don't factor, like x squared plus 1 does not factor, so that that has degree 2. And then in the numerator, you would have to put a degree 1 thing, right? So there's always possible your denominator of the fraction after you factor in everything can be degree 1 or degree 2. It's actually one of the things that we couldn't really say specifically, but any problem that we had a degree 3 or above polynomial back in chapter 3 was always able to be at least factored a little bit. So you won't have like an x cubed in the bottom after you factor ever. X cubed plus 1, for example, factors. But you can always have an degree 1 or degree 2 denominator. Right, but what we'll do, I have 3 examples in this section to show you. One is kind of the easy type of example here, where each factor in the denominator is just to single power. They're both degree 1. Then I'll have one where when you factor it, you have our multiplicity 2 on one of them. And then I'll have another one where when you factor it, you actually have a degree 2 thing. So like an x squared plus 1 in the denominator that doesn't factor. Now, when I say easy, I mean relatively easy. I'm showing you the hard version of the easy ones. I don't know how better to word that. But in the homework, when you have the expressions here, not all of them, all the denominators are necessarily hard to factor, right? But what all we're doing in this first section is setting up a partial fraction decomposition. We are not even trying to solve it yet. We will solve it in the second section, but I just want to set them up first. All right, so the setup, the first thing, this will kind of guide you if you remember. The first thing to do is to factor the denominator. If it's not already factored for you, I guess you can kind of look down and see the second one's already factored for us, but this first one definitely isn't. Factor the denominator if needed, and then we'll go from there. All right, so I'm not even going to worry about the numerator. It doesn't matter at this point. So I got to factor the 20x squared plus 29x plus 5. Now this one is not that great to factor as far as, what's going on here. But I'm not going to, since you've done factoring a lot in your math lifetime, I'm not going to boil down the brutal details like I normally do. I'm just going to remind you can factor this guess and check, AC method, a number of ways, whatever way you want to do it, but you have to do the non-normal way because the front number is not just 1, it's 20. Right, but 4x and 5x will work if you put a 5 over here and a 1 on that one. Right. Now, I've done this so many times that even though I didn't come into this knowing how to do it immediately, I just kind of saw that if I get 25 and 4, that'll make 29. Okay, but remember the way to think about it is you multiply the 20 and 5, the a times the c to get 100, and you want two numbers that multiply to 100 and add to 29. So that's where the 25 and 4 came from. And then you have to figure out how to make 25 and 4 happen when you FOIL. Right, but that's factored. Now the numbers like the 4x and the 5x don't matter because these are each degree 1. And has multiplicity 1. Right. So once again, we're referencing some stuff from chapter 3 here. The multiplicity, once again, just refers to the power on the outside. What that means is we are going to have two fractions. We have one for each factor, and since they have multiplicity 1, it is just one for each factor. So two fractions. One thing I actually like to think about the total number of fractions is you can just add up the multiplicities and that'll tell you the total as well. Okay. All right, so the way we set it up, I'm going to make a fraction. I always add in between because when you set this up, if you do a minus sign, when you solve for your stuff, your numerators, which we'll get to in the second part, and it's just going to change the sign. And the easiest thing to do is write a plus here, because if you write a minus and then you forget to actually distribute that minus through, then you're missing something and already short. So we're going to have two fractions added together, the 2 coming from the, but that's not how you spell the 2 for together. But we have two fractions because of what we mentioned here. One of the denominators is 4x plus 5, and the other one is 5x plus 1. Right. Now to fill out the numerators. Once you fill out the numerator, you have it set up. Now notice here that each of these is degree 1. So each numerator is degree 1 less or 0. And these are just, a degree 0 polynomial is just a number. Now we want to represent that number with a letter because that's what we're going to solve for. And I start with A and then just go through the alphabet for how many letters I need. So A and B are what I used. All right, but I don't want to talk about actually solving them yet. I just wanted to really emphasize setting them up. And this is how you set it up. All right, this is the setup. Next section, we will solve for A and B. But really, for most problems, once you set them up, it's not terribly hard to solve for your missing letters. There can be some subtle things that make it a little more challenging, but the reason I want to separate it is the way you solve for them is not obvious the first time you see it, and I don't want to put more on you before we actually set up the other types of examples as well. All right, so I will, for all three of these, go back to and reference them when we solve them. So make sure you have it written in your notes. All right, the next one we want to set up, same deal. And we don't care about the numerator. Once again, you do not care about the numerator when you start. We have to factor the denominator, but it's already factored for us, which is pretty nice. It doesn't have to be. It's already done for us. We have x squared times x plus 7. Okay. Right, now this is the example that I was talking about above where you have to be careful. So x squared just looks like an innocent degree 2 polynomial, which is not wrong to think about. But you have really a degree 1 polynomial of x with multiplicity 2. And while we normally wouldn't think about it like that, I'm going to think about it like being x minus 0 squared. A degree 1 polynomial, which is the x minus 0, with multiplicity 2. All right, so the way this is set up, I'll scroll up here since we didn't talk about this specifically, but if a factor has a multiplicity, then it will also make that many fractions. So since x minus 0 squared has multiplicity 2, it will make 2 fractions. The x plus 7 is like the example from above. It's just multiplicity 1 with degree 1, so it has 1. And that means we will have 3 fractions total. Since we have the multiplicity added together. Oops. All right, so I'm gonna do what I did last time. I'm gonna start by just adding 3 fractions together. Now, because the x plus 7 is the easy one that we kind of dealt with, I'm just gonna put that here first. Then the other 2 fractions are gonna come from the x squared, but I'm gonna, once again, think about it as x minus 0 squared. We start off with just the multiplicity 1. So one denominator is x minus 0, and then the other denominator is x minus 0 squared, the multiplicity 2 part. Right, so it makes 2 fractions. One is just the inside, and then the next one is with the squared. And like I said, if you had a cubed, which you should not see it at all, but if you had a cubed or a fourth or a fifth power, you would just keep adding. So if we had a cube, we'd have plus another fraction, it would be x minus 0 cubed. Right, but the important thing is that even though this looks like it has degree 2, we only care about the inside. X plus 7, x minus 0, and x minus 0, the insides all are degree 1, which means the numerators are all degree 0 again. All right, so I'm going to give them 3 letters here. I'm going to call them A, B, and C. Now, normally I wouldn't write the x minus 0 because it makes it more complicated looking when you go to try to solve it. So I'm just going to simplify the x minus 0s to x. But this is the setup here. Okay. But once again, if you have a repeated multiplicity, which basically means if you have a power on the outside of a factor, and x squared is really the weird looking example. When you have like x plus 1 squared, it's more obvious, or x plus or minus anything. That's why I wanted to do x squared in the video. But if you have a repeated multiplicity, that means there will be that many fractions. Okay, so if we had a squared on the x plus 7, then there would be also a fourth fraction for x plus 7 squared on the bottom. Right, but this section really, as far as what its intended use is meant to be an introduction to partial fractions, not the full-blown thing. So we won't deal with too many complicated examples. Number 2 and 3 are really going to be as hard as they get. Right, so we have an example where there's a higher than 1 multiplicity. The last example here is going to be one where there's a degree 2 and a denominator that does not factor. Right, but once again, we are setting this up. And here, the denominator, once again, is very nicely factored for us. And any of the ones that are factored in here, I took straight from the homework. I'm not trying to make a shortcut for the videos. So there are plenty of the problems in the homework that are already factored for you. Right? But it's already factored the denominator. Once again, the numerator doesn't matter. Right? Now, the first thing I'm going to point out here is each has a multiplicity 1. So there's going to be 2 fractions because it gets 1 for each multiplicity. All right, just compare that to above. X squared, we can write as x minus 0 squared. X squared plus 2 cannot be factored. The reason we know it cannot be factored is if you try to set it equal to 0 and solve it, you get imaginary numbers. So that's why we don't have to do anything extra here, but I will go ahead and write that down. X squared plus 2 cannot be factored since x squared plus 2, anytime you have something and you want to know if it can be factored, if you set it equal to 0 and try to solve it, if you get imaginary numbers, then it cannot be factored. And so x squared minus 2 would be fine because when we have a minus 2, then we add and get a plus 2 and then do the square root. But when you have x squared plus 2, when you subtract the 2 and then do the square root, you're trying to do the square root of a negative number. So it cannot be factored. All right, so there will be 2 fractions, 1 for each denominator, x minus 8 and x squared plus 2. Now the one on the left is the same kind we've been dealing with. It's degree 1. So the top is going to be degree 0, which I'll just use with the letter A again. But the second one is very different. This is degree 2. This is not degree 1 with multiplicity 2, it's degree 2 multiplicity 1, specifically degree 2. Now what we have to put on the top is a degree 1 polynomial, because it has to be 1 less than the denominator. Right, well, what does a degree 1 polynomial look like if it's generic? Well, it's not that complicated. A degree 1 polynomial is just a linear function, but the way you can write it is well, we're already using a, so let me not use the same letter. But think about like y equals mx plus b. That is a generic degree 1 polynomial. But instead of using m, I just like to go in order of the alphabet. So this is a generic degree 1 polynomial. The easiest thing to forget, I think, for most people is the c part, because you put the b with the x and then kind of forget about the c part. But do keep in mind that when you write a generic degree 1 polynomial, you start with the power of 1 and count down to the power of zeros. So we have a degree 1 part and a degree 0 part. So, definitely, like I said, these last 2 examples for most people are much harder when you're learning than the first example where you just have degree 1, multiplicity 1, it's all perfect. But, these are things that can pop up too. All right, now, since I have so many colors here, I'm just going to rewrite it in black, but I'm not changing anything because there's nothing to simplify. This is our setup. X squared plus 2, not c. That c above threw my eyes off. Right? But what we're going to do now, go in the same order. So this first one, I'm going to solve for a and b. The second one, I'm going to solve for a, b, and c. The third one, I'm also going to solve for a, b, and c. Once you solve for the letters, you just plug them back in, and then that's your answer. Okay, but that's the goal here. You set up, and then you solve. Now the main steps here are, they're not necessarily having to be done this way. This is the way I do it because I like to do the same thing every time, but I also think this is the simplest way. You might run into other people if you get tutoring help on this that do it a little differently. You might like that other way more than my way, and that's fine. But I just do it the way that is simplest for me. All right, so the first thing you have to do when you want to solve, this is pretty much the standard for everyone should show you this, is multiply through by the denominator of the original so that all the fractions are gone. Pretty much everyone will do this. Now this is where I like to do it this way because I think this is the easiest way. It can definitely be the weirdest way at first when you've not done something like this. But what I like to do is plug in x values that make it easy to solve for your coefficients. And you'll see what I mean by that. Now, sometimes you can plug in numbers that doesn't make it super easy to solve for your coefficients, but you can still do it this way. The reason why this way is shorter than the other ways is if you do it the other ways, you don't have this benefit of making it easier sometimes. But then once you solve for your coefficients, you plug them into your final answer and you're done. All right, so let's go ahead and look at this. This is our first one from above, and the setup here, negative 14x plus 35 over 20x squared plus 29x plus 5 equals, now I'm just going to scroll back up, we got a over 4x plus 5 plus b over 5x plus 1. So what I'm going to have is a over 4x plus 5 plus b over 5x plus 1. This is our setup from before. Now, if you're working this on the homework, you would have done the setup part and then start solving it right away. The homework's not really broken down into its separate parts. Now, one thing is that the reason multiplying by the denominator on each side, so this thing, works well is because this is just made up of these factors. So remember that the 20x squared plus 29x plus 5 equals 4x plus 5 times 5x plus 1. Right? These denominators didn't come out of nowhere. So what I'm going to do, normally I don't do this step because it works the same way every time, but I'm just going to plug that in here so you can see everything cancel when we multiply through. Okay, so very literally, I'm going to multiply everything, multiply all the tops by the entire fraction on the left, denominator fraction on the left. Right, but that is the least common denominator. That's why it works. When we do that, what's going to happen is this denominator is going to completely cancel out. Actually, let me not draw through it though, because then looking at the notes might be hard. But the whole denominator will cancel here, so we'll just have the numerator. And when we multiply this on the denominator, or on the numerator for this part, the 4x plus 5s will cancel. You'll be left with a times 5x plus 1. And then when you multiply it by the last denominator, or last fraction, the 5x plus 1 will cancel, and we have a b and a 4x plus 5 left. All right, now what you do from here, like I said, this is where many people will do different things to solve. I'm just going to show you what I do, because to me this is the easiest thing. Our goal here is to solve for a and b. And what some people might do, I'll just describe it in words, is they might distribute the a and b through, gather the like terms, meaning find the stuff with just x in it, factor that out and get a coefficient, and then find the stuff without x in it, and then write that together, and then you can set it equal to each part. It's called equating coefficients. I prefer this much easier way, which is because this is supposed to work for every x value, if you plug in a particular x value, your number should still work out. So what I like to do is I like to figure out x values that make these things 0. If I can figure out what x value to plug in to make this 0, then when I plug it in over for everything in the equation, I'll only have b left to solve for because this will be gone. So the question is, what x value makes 5x plus 1 equals 0? And that's a little equation that you know how to solve. Subtract the 1 and divide by the 5. We get x equals negative 1 over 5. So what I'm going to do is plug this in everywhere, and it will let me solve for b. All right, now because of the way this one works, plugging in a fraction, it can be a little messy with the fraction, but just especially with a problem like this, you want to be really careful, so use your calculator as you need to. All right, so I'm going to plug in x equals negative 1 over 5th into the equation. We get negative 14 times negative 1 over 5 plus 35 equals, even though I know I chose this to make this part 0, I'm going to just write it in for this first one. And it looks like that. Right, and once again, even though it's messy, even though it looks like it has a lot, because this is going to be 0, our only letter left to solve for is b. So now just simplify. I'll do the other one over here because we're going to have to plug in another number to be able to figure out what a is. You need both a and b. All right, so the first thing over here, negative 14 times negative 1/5 would be 14 over 5 plus 35 equals, like I said, this is 0. Multiplying it by 0 by anything is still 0, plus b, and then we have negative 4 over 5 plus 5. Right, now if you're comfortable doing this by hand, you'll do it by hand. If you feel like you've done a lot of work, you already learned this new thing of setting it up and you just want to use your calculator, there's nothing wrong with that. So I'm just going to simplify the fraction on each side. The one on the left, 14 divided by 5 plus 35, and then make it a fraction. 189 over 5. And on the right side, we have our b, 0 is useless, and the inside, negative 4 over 5 plus 5. And math fraction, we get 21 over 5. So we have 89 over 5 equals b times 21 over 5. To finish solving for b, multiply by the reciprocal, 5 over 21. So the 5 and 21s cancel, and we got b equals, also I think this, well, at least the 5s cancel. Let's see, does 189 and 21 cancel? Looks like it'd be 9. It is. So b is actually just 9. Okay. Now, what you want to do next, it seems like, okay, I figured out b, now I want to plug it in. You can do that, but because I can also plug in an x value here to make this 0, it doesn't even matter what b is because it's just going to go away. So I'm not even going to worry about plugging it back in right now. Oops, let me not leave that. That would be bad. All right, so the next thing, what number do I plug in to make this 0, this part 0? If I make this 0, then exactly the other thing will happen. B will go away when we plug it in, and then we'll be able to solve for A. And once again, you can solve this, subtract the 5 and divide by the 4, and you get x equals negative 5 over 4. All right, so I'm going to do exactly what I did over here. I'm going to take the equation and I'm plug in negative 5 over 4. So we've got negative 14 times negative 5 over 4 plus 35 equals a times 5 times negative 5 over 4 plus 1. And then because I chose this to be the number that makes 0, if you plug it in here, we'll get the 0, just like we did last time with the other term. All right, so I'm not going to actually write it out, mainly because I'm out of room over here and I don't want it to look confusing. But it's going to be 0. Now do the same thing as last time, simplify it and solve for a. All right, so the thing on the left here, we've got negative 14 times negative 5 divided by 4 plus 35. Let's just make it a fraction just to keep it simplified. We have 105 over 2. And on the right, we've got a times, and then we got 5 times negative 5 divided by 4 plus 1. And then make that a fraction, and we got negative 21 over 4. So we've got a times negative 21 over 4 on the right. Multiply by the reciprocal, negative 4 over 21. And then we'll only have a on the right side, and on the left side, the 4 and the 2 cancel out. We have 2 on top. That's gone. And then 21 goes perfectly into 105 5 times. So we actually have negative 2 times 5, which is negative 10, equals a. But those were our missing letters. We solved for them. Now that we solved for them, we're done. Just plug them in. But you do need to plug them in. You shouldn't just write a equals and b equals unless that's what the problem's asking for. Right? Sometimes the problems will be set up for you in this way. It's kind of telling you how to set them up, and then it wants you to solve for them. Other times you have to do the whole thing and plug them in. All right, so a is negative 10. That's over 4x plus 5. And b is 9. And that's over 5x plus 1. And that is our answer. Now, just to kind of elaborate why I like my way so much more than the equating coefficients way, is that you saw once we plugged in the numbers that it was pretty quick. Yeah, there were fractions for this one. There's not even always fractions. And then they're not really much to deal with. Hopefully at this point you're a little more comfortable with fractions. But when you equate coefficients, even if the numbers come out nice like this and there's not fractions in your final answer, it always takes a few minutes, and you always have to solve a system of equations that you make from rearranging. So, my opinion, this way is better. That's why I showed it to you. All right, number 2. Once again, we set this number 2 up from before. Now we're going to solve it. So just as a reminder, this equaled, I'm going to write it in the same order that I did above, number 2. We have a over x plus 7 plus b over x plus c over x squared. Now, if you're doing this problem or you're doing one on the homework and you ask the question, does it matter what order I pick them in? No. If you had x and then x squared and then x plus 7 and your a, b, and c were kind of jumbled up compared to this, you would still get the same answers. Your a, b, and c would just be adjusted. Whatever number becomes on top of x plus 7 will be on x plus 7 regardless of the letter you choose. So don't worry about that aspect. right, but this is already factored, and just like from before, we want to get rid of the fractions by multiplying through by the denominator over here. X squared times x plus 7 to each numerator. All right, so when we do that, when we multiply the x squared plus 7x to each numerator, the left side, the whole denominator cancels out. So we got x squared plus 74x plus 28 equals, when we multiply the x squared times x plus 7 to the first fraction here, the x plus 7's cancel, and we get an x squared on top. When we multiply the x squared times x plus 7 to this second fraction here, one of the x's goes away, but we still have another one of the x's. So we got b times x plus 7. And then when you multiply the c, or multiply the x squared plus 7, x plus 7 to the c over x squared, then the x squareds perfectly cancel, and you have just x plus 7. All right, now I want to do the same thing. I want to solve for a, b, and c. Like before, I'm not even going to distribute and simplify anything. I want to go ahead and just pick some numbers that will help me solve. And you're only going to be able to solve for one at a time, so it's going to at least take 3 numbers to plug in. Now, one thing you'll notice is that if you plug in 0 here, the a term will go away, and the b term will go away. The c term will remain because when we plug in 0, that will give us 7 inside. But this x here and the x squared here will make those go away. So I'm going to plug in x equals 0 to make me be able to solve for c. We got 0 squared plus 74 times 0 plus 28 equals, and just like last time, we don't really need to write down the stuff that we know is going to be 0, but just for this first one, again, not a bad idea. But all this boils down to what? On the left side, we have 28. On the right side, we just have c times 7, or 7c, because this is all 0. And then we divide each side by 7, and we get c equals 4. I don't want to preserve room, so that's why I'm writing it over there. Right, but like last time, we're not going to plug in anything. Just going to hold on to that for now. All right, so we solve for c. We still need to solve for a and b. Think about what other number would be a good idea to plug in. Well, if you plug in -7, then this will become 0, and this will become 0 because of the x plus 7's, and we'll be able to solve for a. So let's do that now. All right, so we're, a good indication, you can always look in the, the original fractions anyway and see what should I plug in. What will make them 0? Well, -7 will make this 0, 0 will make this 0. So those are the two numbers I knew I was going to plug in right away. All right, so we've got, dyslexia. We got -7 squared plus 74 times -7 plus 28 equals, like I mentioned, all this is going to go away besides the a part because it doesn't have an x plus 7. But might as well just write it out. All right, so you can see this is 0 here, this is 0 here, so these are going to go away. -7 squared is 49. The right side is just 49a, and then the left side, definitely because of that 74, I don't want to accidentally make a little mistake here, so plugging it in to the calculator, got -7 squared plus 74 times -7 plus 28 equals negative 441. And then we divide that by 49 to get A. And that looks like it'd be 9, negative 9. It is. So we got A equals negative 9. Right, so we've got A and C. We still need to solve for B. Now, if you're kind of thinking about, okay, what's the next best number to plug in? What you're going to find is that you're not going to get something as easy to get everything else to cancel out, because the only two numbers that make stuff cancel are 0 and negative 7. So, and this happens every time you have a repeated multiplicity like that, is you're going to have to plug in another number and solve. Now, since the plugging in another number will not make stuff cancel, you're also going to plug in your A and C. So to solve for B, this will only happen when you have, well, it'll happen when you have a repeated root like this. To solve for B, what we want to do is plug in C equals 4, A equals negative 9, and any other x value that's not 0 or negative 7. Now, the smart thing is to plug in small numbers that are easy to work with, because you can plug in anything. I'm going to plug in 1. Right, I would like to plug in 0, but we've already used it, so we can't reuse it. I'm going to plug in 1. Right. If you plug in, 0 again, this is going to happen again. You're going to get the same thing. So naturally, it's not going to be helpful. But we're going to plug in all of these things. So the left side of our equation, they have x is 1. So we got 1 squared plus 74 times 1 plus 28 equals a, which is negative 9, times x squared, which is 1 squared, plus b, which is what we're solving for, times x, which we're plugging in 1, times x plus 7, which also, again, plugging in 1, plus c, which is 4, times x plus 7, and x is 1. Right, you can plug in any number here. B will come out to be the same, but 1, probably the easiest number to work with besides 0. So that's why I chose it. Now you'll notice, I just kind of want to mention here, I'm not going to write it down for the sake of space and everything, and it doesn't really need to be written down. But if I didn't plug in what A and C are, what would happen is that this would be, A times 1 and C times 8. So you'd have A, B, and C still left in your equation. So that is why we plug in the A and the C. Right, it wasn't necessary to figure out, plug in C to figure out A, because there was still a number that made it go away. But now there's no more numbers to make things disappear. All right, so the left side here, we got 1 squared plus 74 times 1, which is 1, or 74, plus 28 is 103. On the right side, actually, this is small enough to work with. We don't need our calculator. Negative 9 times 1 is negative 9, plus b times 1 times 8 is 8b, plus 4 times 8 is 32. And then combine these like terms, 32 and negative 9 add to 23. We got 23 plus 8b. All right, so we've got 103 equals 23 plus 8b. I'm just going to write 100 equals 103 again. Divide or subtract the 23. We get 8b equals 80. And then divide by the 8 when we get b equals 10. Make that look more like a 0. All right, but that is our b. So we've got our A, B, and C. And once you've got them, then plug it in. A is -9. B was 10. And C was 4. Okay. And that is our partial fraction decomposition of this one. All right, so do keep in mind that as far as the way the setup on the homework is, most problems are like number one multiplicity of 1, and each has degree 1. But if you have a multiplicity, or for the next one, if you have a degree 2 thing, there is a little extra that you have to be careful on. All right, but number 3 here, we've got the third one we set up, 9x squared minus 31x minus 64 over x minus 8 times x squared plus 2. Once again, I'm writing it in the same order as before so I don't mix up my letters. We got a over x minus 8 plus bx plus c over x plus x squared plus 2. Same deal as before. Multiply through by the denominators to get rid of the fraction. All right, so we're going to multiply everything by x minus 8 times x squared plus 2. When we do that, the left side we're just left with the numerator, 9x squared minus 31x minus 64. And then on the right, when we multiply the x minus 8 times x squared plus 2 to the first fraction, the x minus 8's cancel, and we got x squared plus 2. Plus, and then this is a bx plus c, so I'm going to write parentheses around it to make sure we distribute what we're multiplying, or visually distribute at least. And then when we plug in or multiply through by the denominator, the x squared plus 2 and x squared plus 2 cancel, we have just x minus 8. All right, so we've got it set up like last time. And we once again want to ask ourselves, is there a smart number for x to plug in to be able to solve for something? And there is at least one. That number is 8. Because if we plug in x equals 8, this goes away. It doesn't matter what this is then. This goes away and we'll be able to solve for A. So we're going to plug in x equals 8 first. And just to emphasize why it doesn't matter. Oops, that's one too many parentheses. Why it doesn't matter for this second one here, even though we have the B and the C and everything, just to write it in. All right, so the left side, pretty big number, 9, that's not a 9, 9 times 8 squared minus 31 times 8 minus 64, 264. And on the right, we got a times 8 squared plus 2, which is, if we had done that, 66. And then this is all 0, because it doesn't matter what b and c are, we're multiplying by 0. All right, and then we divide through by these. I'm not even going to keep the plus 0 there. We're going to divide through by the 66, and 264 divided by 66. Let's hope that's a nice whole number. And it is. It is 4. So A equals 4. Okay. But we still need to solve for B and C. And one thing you might immediately be thinking of is, well, we've only solved for one number now, and there's not another nice number to plug in. And you are right, there is not. Once again, if you look at the original denominator to tell you what nice numbers to plug in, this, we can plug in 8 to get 0. There is no number we can plug in to make x squared plus 2 equals 0. So what that means, like last time, when you have no more nice numbers to plug in, you want to plug in the a value, the one that we've already solved for, and then choose an x value to plug in as well that's not 8. So we're going to plug in with an x value that is not 8. Now, because 0 wasn't used, that makes me very happy because 0 is great to plug in. So we'll start by plugging in x equals 0 and see what happens. All right, so when we plug in x equals 0 here, what happens is that this whole thing, well, at least on the left side, we just get negative 64. On the right side, a is 4 times 0 squared plus 2 is 2 plus b times 0 plus c. We don't know b or c, so we've got them both there. And then x, once again, we're plugging in 0. Okay. Now simplify this. This is another reason plugging in 0 is great, is even though it doesn't make a whole factor cancel out, look what happens here is that at least b actually goes away, and we will only have c. We got negative 64 equals 8 plus, the inside of this is just c, times negative 8. Subtract the 8 from each side, we get negative 72 equals negative 8c. And then we divide by the negative 8 and we get c equals 9. Right, so kind of similar to last time. We had to plug in a different x value and an a right away, but we did at least get part of it. And that will always happen for you, which is really nice. Well, not always, but as long as you pick the right number, you should always get some number canceling out, even if it's not the whole factor like this, when you have a degree 2 thing. But now we need to solve for b. You should be thinking exactly like kind of what we did last time. When we solve for b, we definitely don't have any nice numbers left to plug in because there's nothing we can do to make a and c both go away. If we plug in 8, then b goes away as well, so that's no good. And we don't want to reuse that number. And there's not a number to plug in to make a go away. So now we're going to plug in any other x value, which I'm going to use 1, along with c equals 9 and a equals 4 to solve for b. All right, so plugging it into our equation here, we got x equals 1. We've got 9 times 1 squared minus 31 times 1 minus 64 equals a, which is 4, times plugging in 1 for x. We've got 1 squared plus 2 plus b. We're plugging in x equals 1 plus c, which is 9, times, I'm running out of room here. I'm going to erase it and write it farther over because I don't want it to look more confusing. So my apologies. Not trying to make this take longer than it has to when you watch it. All right, so reset, we're plugging in 1 for x. That's our left side again. The right side, we have a is 4 and x is 1. B is what we're solving for. Plugging in 1. C is 9. And then for x, we've got, once again, we have our 1 is what we're plugging in. And now you can see we have everything plugged in for except b. We'll be able to solve for b. Just take care of the left side. That's just 9 times 1 minus 31 times 1 is 31 minus 64. is negative 86. And then on the right side here, we got 4 times 3. We don't need the calculator for that. That's just 12 plus the inside of here, b minus or plus 9 times negative 7. Right, and it's totally up to you how you solve it from here. You solve equations like this plenty of times. You can distribute the negative 7 or you can subtract the 12 and then divide by the negative 7. It's totally up to you. I'm going to, for the sake of space here, subtract the 12 first because it should be a little bit quicker. And negative 86 minus 12 should be negative 98. It is. I subtract 12 from each side, and we got b plus 9 times negative 7. Then divide each side by that negative 7. And that should be 14, and it is. So we got 14 equals b plus 9. And then subtract the 9 from each side. 14 minus 9 is 5. We get b equals 5. All right, but I put that in pink, so let me go ahead and box that in the same color. We got our A, B, and C. And now we have our A, B, and C. We plug them in here, and we are done. A was 4, B is 5, C is 9, and we're done. All right. So this would be our partial fraction decomposition. Now I know just looking at how long this video was, I didn't realize it's actually over an hour, and we only did 3 problems. But do keep in mind that I went very slowly explaining every step. Once you practice these a couple times, especially the first type of example, you can probably knock them out in each one in about 5 minutes. These problems like number 2 and 3 here with the higher multiplicity or the degree 2 might take you a little bit longer. But the homework's only I think like 8 questions or so. So hopefully it doesn't take you too long. And read the question carefully. Sometimes it only asks for the A, B, and C. They'll probably call them something else. It depends on the homework. Other times it might ask for the whole thing. Partial fraction decomposition, so just be aware of that. But that is our section 9.4.